In this video, I'm going to prove that if I had wanted to add up consecutive numbers up to a particular number, n, I could have found that answer by taking n, timesing it by n plus 1, and dividing that all by 2. Now you'll remember that we had to follow certain steps when following proof by mathematical induction. And our first step is to prove that the statement is true for n is equal to 1. If we're going to do this, we have to prove it for the left-hand side and for the right-hand side of the statement. On the left-hand side, if n is equal to 1, then my answer is 1. On the right-hand side, if n is equal to 1, then I'm going to get 1, all times by 1 plus 1, and then all divided by 2. 1 plus 1 is 2, 2 times 1 is still 2, and 2 divided by 2 is 1. In other words, we have proven the statement true when n is equal to 1. You've only finished the first part of your proof when you write up your conclusion. So you must say that the statement is true for n is equal to 1. We're now going to go on to the second part, which is our induction. And you remember, you start with your assumption. You'll remember that for our assumption, all we need to do is we need to make n is equal to k. This is very simple. If I write n is equal to k, I therefore am going to write 1 plus 2 plus 3 all the way up to where I had an n, which is now going to be k. And then on the right-hand side as well, wherever I see an n, I replace it as well with a k. So I now have k plus 1, all divided by 2 on the right-hand side. The second part of our induction is to prove that the statement is going to be true for n is equal to k plus 1. And we're going to do that next. As I'm going to be doing a proof, I need to understand what I am going to be proving. Let's take a look and see how I would write down the proof. I want to prove the following. I want to prove that if I take 1 plus 2 plus 3 and I go all the way up to k, but now instead of just k, I'm going to have k plus 1. So I'm going to go up to k plus 1. And then I must find that this answer would have been given to me if I replace the k, which was the n, with now a k plus 1. In other words, if this is going to work for the very, very last domino, on the right-hand side where I've got a k, I must now write k plus 1. And when I had k plus 1, I must write k plus 1 plus 1, and that's k plus 2. And this is still divided by the constant of 2. Now, as I'm going to be proving, I want to prove that the left-hand side can look like the right-hand side. On the left-hand side, I'm going to fill in one more small piece of information. Can you see that the original statement over here went up to k? If I'm going to go all the way up to k plus 1, I could have written up to k and then k plus 1. In other words, this statement over here now matches with the one that I had in my assumption. If the part that I've underlined in green is the left-hand side of my assumption, that must be equal to the right-hand side of my assumption. So that's what I'm going to start with. In my proof, I'm going to definitely start on the left-hand side. Looking at the left-hand side, if I take 1 plus 2 plus 3 plus all the other numbers plus k, I could have written that as k plus 1 divided by 2. And the last number, which I couldn't underline in green, is going to be k plus 1. Now, as the part that I'm looking for on the right-hand side has got a common denominator of 2, I need to write this whole expression that I've now got for the left-hand side also with a common denominator of 2. As the second part of the expression, the second term, had a denominator of 1, that is the part that needs to be times by 2. So if everything is all over 2, I still have k, and then k plus 1 for the first term, but then for the second term, I need to times that all by 2. In my next step, I'm going to simplify the numerator. So in my numerator, I now have k squared plus k plus 2k plus 2 all over 2. If I add like terms in the numerator, I'm going to have k squared plus 3k plus 2 all over 2. Now, can you see that there's a very nice bit of factorizing that you can do in that numerator using your trinomial factorization? If you do that, you're going to find that you're going to get two bracket factors. The first one is going to be k plus 1, and the second one, k plus 2, and that's all over 2. Now that is equal to my right-hand side. In other words, I've proven the statement is true when n is equal to k plus 1. Remember, it is critical for you to write up your conclusion. So you must say that the statement is true for n is equal to k plus 1 if n was an element of your natural numbers. And finally, the last part of the formal proof, when proving by mathematical induction, you state that as the statement is true for n is equal to 1, and the statement is also true when n is equal to k plus 1, the statement must be true for n is equal to k if n was an element of the natural numbers. This concludes our formal proof.